Talk about new class of graphs, perhaps, right?
Thank you.
Well-partitioned chordal graphs.
Okay, thanks for the introduction. Today I'm gonna introduce a new subclass of chordal graphs called well-partitioned chordal graphs, and we'll explain the characterization in terms of forbidden-induced subgraphs, and we'll briefly explain its application. This is a joint work with Lasse Paloma Lina in University of Bergen and Jungho Ahn in International University and IBS. Let's first remind the definition of chordal graphs and split graphs. A graph is a chordal if it has no induced cycle of length at least 4. And a graph is a split graph if its vertex set is partitioned into a clique and an independent set. So in this figure, the left graph is chordal. You can easily verify it has no induced cycle of length at least 4. And here, this is a split graph because we can partition the vertex set into first the center 5 vertex, which form a clique, and all the surrounding vertices is an independent set. So this is a split graph. And it is known that split graphs is a subclass of chordal graphs. So what is the well-partitioned chordal graphs? So first, let me briefly give you some intuition of the definition. So in this figure, I partition, so let's remind that this is a split graph, and I partition this split graph into 4 bags. So the one bag is for the center clique, and the other bag is one bag for each vertex in an independent set. Then you can see a star-like structure in these bags, right? So all surrounding bags is adjacent to the center bag, so they form a star structure. So we're going to generalize this structure into well-partitioned chordal graphs. So well-partitioned chordal graphs generalize split graphs in 2 ways. First, these cliques can be partitioned in a tree-like structure instead of a star structure. And even more, each clique can have more than one vertices. Right? So let's see the formal definition. A connected graph G is well-partitioned chordal if there exists a partition P of the vertex VG and a tree T called a partition tree, which is the most important definition in this talk, having P as a vertex set such that each partition X is a clique, and it will be called a bag of G. And 2 bags X and Y are adjacent in T if and only if there are some subsets X prime and Y prime of X and Y respectively, so that all edges between these 2 bags are just coming from X prime and Y prime. It means that in this figure you can see that this vertex and these 3 vertex form a complete bipartite graph between these 2 bags. And if 2 bags X and Y are non-adjacent in the partition tree T, then it means that there are no edges between these 2 bags. So basically, all edge incidents coming from the tree structure here. And additionally, I will use this notation, BD, B1, B2, means the boundary of B1 into B2 is the set of vertices of B1 that have neighbors in B2. So in B1, these red vertices, can you see the color? These red vertices are the only vertices that have neighbors in B2. So I will denote by BD, B1, B2, the boundary of B1 into B2. Okay? And usual graph G is a well-partitioned chordal if all of its components is well-partitioned chordal. Right? Any question? No?
I was just wondering if this is the same as if we would just say it's a tree decomposition into cliques.
Tree decomposition into cliques.
Yeah.
No, because these intertwined edges should be captured in some back.
Yeah, I mean, sure, but you can easily extend extend each bags with their neighborhoods, and then that would be a tree decomposition into cliques, right?
Yeah, I think so.
The notion
Yeah.
of these should be the same, maybe.
Yeah, it might.
Am I missing something?
Yeah, it might be. Yeah.
Well, the non-adjacent bags have any neighbors and edges between. The tree decomposition may have a common one. The tree decomposition could have some logic appearing in many bags. Yeah.
Actually, it is known that for chordal graphs, we can construct a 3D composition on which every bag is clicked. So I think that we can easily modify this partition tree into some 3D composition. But fortunately, this talk is nothing to do with this 3D composition. Yeah. Okay.
The condition 2 is the main difference between the use of 3D composition and
condition 2.
I guess that's between two bags. There are some vertices that all crossing edges exist in the graph.
Yeah, yeah.
But in tree decomposition, it doesn't have to be.
Yeah, right. Our partition tree is different to the 3D composition tree. So maybe we.
I think it's a special paper.
Yeah. Okay. Let's think later. Yeah. But the original definition itself is nothing to do with the 3D composition. Yeah. Anyway. Okay. Let's see some motivation. The motivation basically comes from computation complexity. So some problems are easy on split graphs and while hard on chordal graphs. Also, there are some problems we don't know their complexity on chordal graphs. Then one question naturally arises that until which subclass we can ensure that this problem remains easy, or on which subclass we can show that some problem is hard so that we can investigate its complexity on chordal graphs. So one question is that how tight can you narrow down the complexity gap between chordal and split? So that's the motivation of well-partitioned chordal graphs, that is to narrow down the gap and reveal unknown complexity on chordal graphs. One may wonder whether we can apply meta theorem on these well-partitioned chordal graphs, but unfortunately we can't. Yeah. First, the meta theorem saying that Kusel proved in 1997 that on a class of graphs having bounded trees, every graph problem expressible in monadic second-order logic 2 can be solved in polynomial time. And in a clique version, every graph problem expressible by MSO1 can be solved in linear time. But Mengele showed that the class of split graphs has unbounded memories, and in the thesis of Bashar, he showed that for every graph G, memes is a low bound for trees and clique widths. So even on split graphs, we can easily apply meta theorem. So when we are dealing some problems on superclass of split graphs, we have to solve each problem manually.
Sorry, what is the name?
Okay, yeah. Memes is defined by some branch width. So basically, when we see some code, we count how many, what's the largest size along this code. So, but the important thing is that this matching should be induced in some sense, and semi-induced. So, if we find these 5 edges among which no other edge arise, then we'll say this mean value is 5 of this code. and want to find some decomposition that has a small this mean width. Yeah. Okay. And before to present the main result, let me remind some definitions in complexity. So let pi be a decision problem. Pi be a problem, or it might be a decision problem, parameterized by some parameter k, having input size n. And pi is a slice-wise polynomial, or xp, if it admits an algorithm of running time fk times n to the gk. So it means that when we slice the input space by picking some specific parameter k, then it can be solved in polynomial time. And if g is a constant, then we say that the problem pi is fixed parameter tractable, so FPT. And it is known that a decision problem pi is FPT if and only if it admits a kernel. So what's the kernel? A decision problem pi admits a kernel if it admits a polynomial time preprocessing algorithm that given an instance I, k returns an equivalent instance whose size is bounded. And if this bound is polynomial, then we say that pi admits a polynomial kernel. So here equivalent means that the original instance and the resulting instance say always the same answer. Okay, now let's see our result. So this is a known complexity result among split graphs and chordal graphs. So I'm not going to rigorously describe all this problem, but we'll focus on this complexity result. So for dominating set problem and max curve problem, it is known that these are NP-hard even on split graphs. So they are still NP-hard on each superclass. But there are many problems which can be solved in polynomial-time solvable and admit some polynomial kernel. So B-chromatic numbers, sparse the K subgraph, dense is the K subgraph, are known to be polynomial-time solvable on split graphs and are NP-hard on chordal graphs. But even more, 3-3 spanner is known to be polynomial-time solvable on split graph, but its complexity on chordal graph is not known yet. And similar to GEODETIC set, and disjoint passes and set restricted disjoint passes, which is a generalization of a disjoint passes, are known to admit a polynomial kernel. But on chordal graphs, it is not known yet. I mean, on chordal graphs, it is known that these disjoint passes does not admit a polynomial kernel under some complexity hypothesis. So our effect of well-partitioned chordal on these complexities is as follows. We still have some complexity gap between split and chordal graphs, but we feel some complexity gap between them. So first of all, Abel et al. Show that B-chromatic number problem is NP-hard on chordal graphs, but in their construction of chordal graphs on which to show the complexity, they actually use well-partitioned chordal graphs. So they indeed show that B-chromatic number problem is NP-hard on well-partitioned chordal. So it means that we have some problem that is NP-hard on chordal graphs, but still hard on well-partitioned chordal. Well, what about the other way around? These four are our contribution, and we show that some problems which are easy on split graphs still easy on well-partitioned chordal graphs. And so, yeah, so we can extend the complexity result to well-partitioned chordal graphs. Okay. So let me give you some rigorous description of our result. We show that as a structural result, there are 8 types of forbidden induced subgraphs of well-partitioned chordal graphs. And in addition, given a graph G, in polynomial time, we can either find a forbidden-induced subgraph or construct a partition tree for G. It means that we can, in polynomial time, recognize well-partitioned chordal graphs. Okay. As an algorithmic results, the first problem we handled is disjoint passes. Two passes P1 and P2 are internally vertex disjoint if for each I in 2, no internal vertex of Pi used in the other pass. So, yeah, okay. And this disjoint pass problem is as follows. Its input is a graph G and some set X of K pairs of vertices of G called terminals. And its goal is to decide whether this graph G contains some K pairwise internally vertex disjoint passes P1 to Pk such that each Pi is an SITI pass, meaning connecting Si and Ti. It is known that Robertson, Seymour, and Kawarabayashi show that disjoint pass problem is FPT. And even more, Baudelaire et al. Show that DP does not admit a polynomial kernel under some complexity hypothesis. But all these results are about general graphs. So what happens if we restrict our site to some small graph class? So Kammer and Helly show that this problem becomes linear FPT on chordal graphs. And Hagen et al. Show that it remains NP-complete even on split graphs, and admit a kernel with quadratic vertices on split graphs. And they ask that whether this problem admits a polynomial kernel on chordal graphs. And our result is that it does, admit a polynomial kernel on well-partitioned chordal graphs. We also handled a variant of disjoint pass problem. Vermont et al. Introduced a generalized version of this disjoint pass as follows. So it is called set restricted disjoint passes, parameterized by K, and its input is the same, but one different part is this U. So we have some predefined domains, U1 to UK, and our goal is now try to find some past Pi so that whole its vertex set is contained in UI. So if every UI is equal to VG, then it is nothing but disjoint pass problem. So it is a generalization of disjoint pass problem. And they show that it is XP on chordal graphs and asked whether it is FPT or W1 hard on chordal graphs. And we show that it is FPT on well-partitioned chordal graph. In addition, we can get some polynomial kernel on split graphs. Yeah, but still, it is open whether this problem there is a polynomial kernel on well-partitioned chordal graphs. Yeah. So it's a summary about our results on these disjoint pass problems. So we show that well-partitioned chordal graphs admit a polynomial kernel, and well-partitioned chordal graphs on which cell-restricted disjoint passes become linear FPT, and we can get a quadratic kernel on split graphs. Here, star means that when we are given a partition tree, then we can solve it in linear FPT. Right? Any question? No? Then let me.
What's the fact? Like you have an algorithm that either finds an obstruction or construct a tree. So if you combine them, do you get the FPT algorithm?
Yes, yeah, of course, yeah. We can recognize well-partitioned chordal in polynomial time. I guess that it's a degree of the polynomial maybe less than 10, but I'm not sure. Yeah, but then the problem becomes not linear. I mean, we can solve in FET, but we don't know yet whether we can recognize well-partitioned coda in linear time. So that's why we put star on here. So if we can construct a partition tree in a linear time, then there is no restriction on this complexity. So, yeah. Thank you. And now I'm going to give you some characterization in terms of probability-induced subgraphs. I say that there are 8 types of probability-induced subgraphs. So here are 4 small obstructions, O1, O2, O3, and O4. And we have a horse, and we have a 3 infinite class of obstructions. So here, the first one is something with 2 diamonds. I mean, a diamond is a K4 without an edge. And if we connect 2 diamonds with some triangle chain, then we call it W1T. And this is one type of the obstructions. And the second one is just substituting this diamond with this weird graph. And I still connect these 2 wings with some T triangles. And the third one is substituting this part with this one, right? So these are all the obstructions for well-partitioned coda graphs. It is not hard to see that they are actually an obstruction because all well-partitioned coda graphs is governed by these 2 rules. So first of all, the vertices of a triangle are in at most 2 backs, because otherwise the backs form a triangle in a partition tree, right? So that's the first rule. And from the rule 1, we can derive rule 2. The diagonal of a diamond means that 2 vertices of degree 3 should be in the same back. Because otherwise, by rule 1, let's say this diamond, and let's assume that they are in the different back. Then by rule 1, these 2 should be in the same back, and these 2 should be in the same back. But then you can see that these 2 backs does not induce the complete bipartite graph between them, right? So the diagonal of a diamond should be in the same back. Then you can easily see that this graph is not a well-partitioned coda graph, because these 2 vertices should be in the same back. But then this vertex is not in the same back because each back is a clique, right? So they should be in the same back, and same back. But then there is no back to be this vertex to be inserted. Likewise, we can easily verify they are actually obstructions. Like this O2, these 2 vertices should be in the same back. These 2 vertices should be in the same back because they are diagonals of diamonds. But then these 3 vertices does not form a clique, right? So that's why this graph is an obstruction. And with this probability-induced subgraphs, we can design a recognition algorithm. So we show that a graph is well-partitioned coda if only it has no induced subgraph isolated one of these graphs in O. And in addition, we can decide whether given a graph G is a well-partitioned coda or not in polynomial time. So basically, we have 3 steps. So the first step is starting from some vertex ordering. So remind that well-partitioned coda graphs are, of course, coda graphs. So some graph is not coda, then it means that it is not well-partitioned coda, right? So we first try to decide whether the graph is coda or not. So and it is known that a graph is coda if it admits the perfect elimination ordering. So what is a perfect elimination ordering? So a vertex is simply sure if each neighborhood is a clique. And so in this graph, this vertex and this vertex is clique. I mean simply sure, right? Because each neighborhood form a clique of size 2. And graph G has a perfect elimination ordering, say V1 to Vn if Vi is a simple issue in Gi, where Gi is a graph induced by Vi to Vn. So let's see the figure. So here, this vertex is simple issue, so I first choose this one. And then, now this vertex becomes simple issue. So I will choose this one, this one, this one, and this one, and so on. So this is a perfect elimination ordering. And Rose, Tarzan, and Ricker show that given a graph G, we can generate a perfect elimination ordering in linear time if one exists. It means that we can recognize chordal graphs in linear time. So we are going to construct a partition tree in an inductive way along this perfect elimination ordering. So that's the step one. Step one is try to find the perfect elimination ordering. And the second step is to find some obstruction or a good structure. So before step two, we may assume something. So first one is we can assume that G is connected, because otherwise we can try to find the partition tree on each component. And we denote by V the simple issue vertex of G. And since we try to construct a partition tree in an inductive way, we can assume that G delete V is well-partitioned chordal. Even more, we can assume that we are given a partition tree. And the most tricky part is phi. Note that if V is a simple issue, then V can have neighbors in at most two bags, because the neighborhood of V is clique, right? So if V has exactly one neighboring bag, then we can easily modify the partition tree to a larger partition tree. So tricky part is when V has neighbors in exactly two bags of T. So I will assume that V has exactly has neighbors in exactly two bags. And in step two, we need some definitions. So in a partition tree T, let X be a bag and B be a non-empty proper subset of X, and we say that G be a vertex in outside of X, and we say that V cross B in X if it has neighbor both in B and X minus B. Right? So if we have a X here and B is something here, and if V has both neighbors in this side and this side, then we say that V cross X. I mean V cross B in X. And remind that for bags B1 and B2, the boundary of B1 into B2 denoted by BD B1 B2 is the set of vertices in B1 that have neighbors in B2. Okay. Then in a partition tree, an ordered sequence of bags XL to X1 is called boundary crossing path if either L is equal to 2 or for each I from L to 3, there is a vertex in Xi that crosses this boundary. So this is a boundary crossing path. I draw some 5 bags, and this small part is a boundary of C5 into C4. And this part is boundary of C4 into C3, and so on. And this is a boundary crossing path because C5 has a vertex that crosses this boundary, right? It has a neighbor in here and neighbor in here. And also C4 has a vertex that crosses this boundary and this the remaining part, and so on. So that's the definition of a boundary crossing path. So everyone understand? Okay. And a boundary crossing path is called complete if the vertex in this boundary is completely joined to the next bag. So this vertex is now adjacent to every vertex in here. And this vertex is also adjacent to every vertex in here, and so on. So in this case, we say that boundary crossing path is complete. And the last one is exclusive, means that there is no other bag Y contain a vertex that crosses this boundary. So this figure is example of a non-exclusive boundary crossing path. Because here is a boundary crossing path specified to C1, but we additionally have another path called C prime that also has a vertex cross this path, right? So in this case, we will say that this boundary crossing path is non-exclusive. And really, last one is good. It means that it's both complete and exclusive. Now, why it is called good? Because if it is bad, then we can do something. So this boundary crossing path is good. Bad. Because there is another path that also has a vertex cross these two parts, right? So this boundary crossing path is non-exclusive, so it's not bad. But then we can find an obstruction inside this graph. This red part is an obstruction, so that's why we call it good. So if we found some bad boundary crossing passes, then we can find an obstruction, and we show by some lemmas that if we found some bad boundary crossing passes ending with the back neighboring V, then we can always find some obstructions. So what it means, then we may assume that we always are given a good boundary crossing passes ending with the back neighboring V. This is the end of step 2. And the last step is to modify previous partition tree. So we know that except V, we are given a partition tree. And imagine that we try to insert V into some bag to get some larger partition tree. But in most cases, it is impossible because I mean, it is not natural to insert V into some bag. So to do this, we have to modify our partition tree so that we can always safely insert V into some bag. And the basic idea is cut and merge. So here, we divide each bag along this boundary and merge them with the previous one. And we do the same thing for the lower part and get a new partition tree. And then we show that in this modified partition tree, we can always either put V into some other bag or to make a new bag containing V so that the resulting partition tree is actually a partition tree. Right? So in each step, remind that in each step, we either find an obstruction or make a larger partition tree. So at the final step, we always correctly recognize well-partitioned chordal graphs. So this is our recognition algorithm for well-partitioned chordal graphs. So now let's see some applications. So our first application is set-listed disjoint paths. And let me remind the description. So we have some predefined domains and try to find some internally vertex disjoint paths connecting them. And we show that this problem is FPT or well-partitioned chordal. And to do this, our strategy is some marking procedure. So we have a partition tree, and what we will do is try to mark some vertices in B. So in along some route, we mark vertices in B. And then we need some definition saying that we say that a back B is feasible if enough number of vertices in B are marked so that we can always find some SITI paths that only use marked vertices. If it is case, then we say that back B is feasible. So I actually used two colors in this figure, but it seems that they are not distinguishable. But yeah, anyway, yeah, sorry, we have yeah, mint and blue. So anyway, yeah, here is S1 and T1 and S2 and T2, and mint ones are U1 and blue ones are U2, right? And we marked some vertices inside this area. But then in this case, this bag is not feasible because notice that we have a S2, T2 path along this area, but we don't have a S2, T2 path using only marked vertices because we have no way to go from here to here, right? So to go further step from here to here, we have to use this vertex. But none of these vertices is marked, right? So in this case, B is not feasible. But if we, but if we mark more, then we can show that in this case, B is feasible. And we show that given an instance with well-partitioned chordal graph, graph G has a desired disjoint paths if and only if every bag of T is feasible. So it suffices to check whether every bag is feasible or not. So from this, we show that this problem can be solved in a FPT time. We also handle some variants of set restricted disjoint passes that these problems can be solved efficiently on well-partitioned chordal graphs, but I'm not going to rigorously describe them. And second application is something about Helly property. So given a connected graph G, for each, given a class C of connected graph for each graph G, we can ask, does G have a vertex that belong to all of the longest paths and cycles in G? So we can easily show that if we have two longest paths, then there should be some vertex that intersect these two paths. But when we try to find the vertex that belong to every longest path, then it generally false. But it is true for some graph classes like this, including split graphs and star-like graphs, which is a subclass of chordal graphs. So on chordal graphs, we show that it is on well-partitioned chordal graphs. So in every connected well-partitioned chordal graphs, we can always find a vertex V in polynomial time that intersect every longest path. And even more, for two connected well-partitioned chordal graphs, we can find a vertex that intersecting all longest cycles in G.
Is it the same vertex?
Yeah, maybe. Yeah. I don't know, but the method is same. Yeah. The third application is tree-tree spanner. So for a connected graph G and a positive integer T, spanning tree T of G is called a tree-T spanner if for every pair V, W of vertices, the following inequality holds. So the distance between V and W in G is at most T times each distance in the spanning tree. And tree-T spanner asked whether given a graph G other means tree-T spanner. Kai and Cornell in 1995 showed that this problem is linear time solvable if T is at most 2. N is NP complete if T is at least 4. But surprisingly, for T equals 3, the complexity of three spanner on general graphs is not yet unveiled. So Grandstadt and et al. try to investigate the complexity on chordal graphs of diameter and most 2. So they show that this tree spanner is polynomial time solvable on chordal graphs of diameter and most 2. But on general chordal graphs, its complexity is not yet unveiled. So what we do is tree spanner is actually polynomial time solvable on well-partitioned chordal graphs. In addition, one can construct this tree spanner in polynomial time. So the remaining question is that whether this problem or whether this tree spanner is polynomial time solvable on chordal graphs. And the last application in this talk is geodetic set. What is geodetic set? Yeah, for a graph G and a vertex set S, the geodetic closure of S is the set of vertices that lie on a shortest path between a pair of distinct vertices in S. So let's see some example. If we have a complete bipartite graph K33, and say that this vertex is S, then we can show that every other vertices lie on some shortest path between 2 vertices of S. So here, this vertex is on the shortest path from here to here, right? And this vertex is on the shortest path from here to here, any kind of pair. And this vertex is on the shortest path between 2 vertices of the S. So in this case, we call S geodetic, geodetic set. I mean, okay, sorry. Let's consider this case. Yeah. So these vertices are covered by some longest path condition of S. So we call this is geodetic closure of this vertex of S. And if this geodetic closure is equal to the entire vertex set, then we say that the vertex set is geodetic set. So the problem geodetic set asks given a graph G, verify the smallest size of geodetic set in G. And rather than I show that this problem is NP hard on chordal graphs. But we show that geodetic set is polynomial time solvable on well-partitioned chordal graphs. In addition, remind that the question itself is just ask the smallest size. But we show that we can find the minimum size geodetic set of G actually. I mean, here we don't have to find the specific geodetic set.
Given the set, we verify whether it's geodetic.
No. Just try to find the smallest size.
Number.
Yeah, number. It's sorry. So yeah, to answer this question, we say some number. Yeah, but our theorem actually construct a minimum size geodetic set. So we can, of course, answer the previous problem. Okay, yeah. So let me summarize our main research. So we have several problems. So, some of them are hard on split graphs. Of course, they are hard on all the superclass of split graphs. But some of them easy on split graphs, but hard on chordal graphs. So we try to fill this complexity gap between split and chordal graphs. That's the motivation of well-partitioned chordal graphs. And we show that these three spanner geodetic set are actually also polynomial time solvable on well-partitioned chordal graphs. But for disjoint passes and disjoint passes, they are NP hard on split graphs. So instead of polynomial-time solvable, we show that they are FPT and also admit a polynomial kernel. And for set-listed disjoint passes, we show that linear FPT. Yeah, but the question whether it admits a polynomial kernel or well-partitioned chordal is still open. So let me start my talk with some open problems. So remind that one question is that the set restricted disjoint passes parameterized by the number of terminals admit polynomial kernel or well-partitioned chordal graphs. And note that chordal graph is characterized by the perfect elimination ordering. So we wonder whether there is some concise characterization in terms of some vertex ordering, like perfect elimination ordering or well-partitioned chordal. This question is somehow motivated by the following question, because saying that can we recognize well-partitioned chordal graphs in linear time? Because our algorithm try to detect some vertex set, and it makes our algorithm super linear. So we wonder whether we can recognize well-partitioned chordal graphs in linear time. And one might wonder the existence of any constant factor approximation algorithm for vertex deletion problem for well-partitioned chordal graphs. It means that if we can delete some amount of vertices to make to find the well-partitioned chordal graphs, then can we always delete some small bunch of vertices so that their deletion leads to some well-partitioned chordal graphs? So this is at the end of my talk, and thank you for your attention.
Thank you very much. Any questions?
Can you go to the application 2?
Yeah.
Yeah, my first question is why does it call Helly property? Usually Helly property is something that if many of them satisfy some property, then the whole family satisfies the property. This just says a vertex that belongs to all of the longest paths.
Okay, yeah. Sorry for that, but then we can think it as some transversal problem. I mean,
No, I agree with the name, because in any graph, any two longest paths intersect. So we have situation where any two longest paths intersect. So the Helly graph will say that then all of them intersect.
Okay. And my second question is, as far as I remember, usually people say Helly graph when we can define the disk. Disk is from a vertex. We look at all induced subgraph on the vertices in this within certain distance from this vertex. That's the disk in graph. And the Helly graph is something like if there is some number that when certain number of disks are intersecting, then all disks have the vertex in common, then it's called the Helly graph.
okay.
Is there results in that direction for this graph?
That's a good question. So in disjoint path problem, we consider some similar situation. So instead of passes, we try to find some disjoint connected subgraph. Connected subgraph instead of passive, so that they are not intersecting to each other. So And we can easily generalize the ideal for disjoint passes to some connected things. So I expect, I'm not sure, yeah, but we can, I expect we can generalize our idea to bind some transversal for long distance passes towards some disk. Yeah. The partition tree has some tree structure, so it makes us to easily find some Helly property. So yeah, I guess so.
Another question is,
yeah.
chordal graphs can be represented as an intersection graph of subtrees.
Yeah. Is
there any special property of this special chordal graph in that flavor?
That's a very good question. But intersection, I mean, chordal graphs can be represented by some intersection graph of subtrees of some tree. So if we have some tree, T, and we represent each vertex by some subtree inside here, and make some intersection graph of these subtrees, then it becomes chordal graphs. So chordal graphs can be recognized by, can be characterized by this intersection model. But we can easily make some partition tree. I mean, this intersection model from partition tree. But in this model, each maximum cliques intersect in very involved way. So when we take some maximum clique, they can make some very complicated intersection. But in our setting, all maximum cliques are clustered in some way. So if we take this bag, then the only maximum cliques contained in this bag is just attaching some boundary to here. So that's the basic difference between this partition tree and this intersection model. Okay. And it give us a very algorithmic usefulness over partition chordal.
So that application. So your methods actually answer this question for some new class, or is it strictly on the algorithm and
Yep.
This thing about there being a vertex and all that on this path.
Mm-hmm.
So it's for this TK2 graphs. But are there any new classes which come out of this?
Yes.
The famous,
Yes. You mean the graph class only it has some this Helly property? Yeah, these graph classes. So first one is trees and most 2, and the second one is circular arc graphs. It's like some interval graphs, but instead of line, we use some circular arc and want to see the intersection model of this graph class. And people sparse graph means that people sparse graph is a graph when we take every 5 vertex, then there is at most 1 induced people. And people K13 free graphs and dually chordal. The definition is weird, but it's something related to clique graph of chordal graphs. And 2K2 free graphs, split graphs, and star-like graphs. And here, star-like graph is an intersection model of some tree where I want to see the intersection between sub-stars in a star, in a tree. And it is known that well-partitioned chordal graph is a superclass of split graphs and a subclass of star-like graphs. Sorry. Well-partitioned chordal graphs are superclass of both of them.
So for 2K2, so this was all
Yeah.
was wondering about this disjoint class algorithm.
Yeah.
One thing I was curious is whether you can use this technique, relevant vertex technique.
Yeah.
So what I was thinking is perhaps if you can find a vertex whose deletion doesn't change the answer, then you can win by repeatedly deleting it until the truth becomes small.
Mm-hmm.
Then you can use the generic algorithm. So if you have fixed number of terminals, pairs of terminals, I was curious whether you can reduce the clique number if the largest clique is too big. If some bag is too big, then maybe you can delete one vertex in the middle so that the answer doesn't change. That will probably be some algorithm which will be probably worse than yours. I wonder whether you thought about that kind of thing.
Yeah, I think that's a good approach. But in our algorithm, when we delete some all irrelevant vertices, there still might be very big clique, whose size is in terms of something like a quadratic of k. So still our that's the tricky part. Yeah, we. Okay.
Any other questions? That's thanks. Speaker again.